dinner, so please stay awake until then. Well, you've seen it in the lab, so now I'm gonna show you a bit more what's behind the scene, and I'm going to talk to you about how to learn to exploit elastic actuator for polyplane locomotion. And my name is Antonin. But first, I would like to motivate a bit what I'm doing. I'm mostly working on learning for real robots, so mostly focusing on reinforcement learning directly on real robots. There's a lot of work on reinforcement learning in simulation and transferring from simulation to real robots. And the question one might be, why would you even do that when you have all the simulator where you can have thousands of robots in simulation and just analyze your training? And one answer is, of course, our simulation are perfect, and that's only what we need. So this is what happens when you optimize for the longest jump in simulation. I ran it during the night, and when I came back, I had a very high reward, and I was okay. Either my reward function is wrong, or something wrong happened with the simulation. So the reward function was right, but there was some trouble with the simulation. Again, another simulator for racing, two-car racing with reinforcement learning, and you will see a very accurate behavior that you can see actually in Formula 1. So when the blue car going to overtake the orange car, everything going to go as planned. So, you know it, there's some simulation to reality gap. But also learning on real robot comes with some its own challenges. So one reason is now, why do I want to learn on real robot? One reason is now we can, because we have both the hardware which is robust enough, for instance in the case of pairs, and we have also the software which is fast and sample efficient enough to actually do that. Of course, simulation is safer, faster. You can try more all new ideas. If you need to jump or do a backflip, you can directly try it. And but if you have a simulation, then you need a very accurate model, and you still need some randomization in order to keep the patterns from simulation to reality. Of course, learning on real robot comes with its own challenges. So you have some safety involved, so both for the robot and for you. And you need to be very sample efficient because you cannot be faster than real time. So it takes quite some time to, it might take some time to learn on the robot, so you need to be careful with your design of the algorithm. I'm going to quickly present BERT and then explain a bit my approach to learn fast on the real robot and also learn multiple gates for also not only one robot, but actually 3 robots. BERT, I've shown it to you this morning, so it's a quadruped with soft elastic actuator, so it's around 3 Nm per rad. And it has serial elastic actuators, so one motor with a torsional spring connected to the joint. And the motor are pretty simple, it's just servo motor, and the max torque that they can generate is pretty small. And you may say, okay, but then you can just learn from scratch. So yes, I did it. I actually, so 3 years ago, I did reinforcement learning on BERT. It worked in 5 hours, 8 hours. It took some time, some effort, some reward engineering. And I retried this year with better algorithm, better software, and a bit more knowledge about the robot. And this is what you can achieve in only actually 10 minutes. So at first it really learns from scratch, so it will do just random movement. And after 5 minutes it will first do its first step. And as soon as it does its first step, then it will manage to walk. But learning from scratch here with a very simple reward, which is maximizing the forward speed, it will plateau actually quite quickly, and then you cannot control the gate that is going to be learned. Actually, the fastest gate, if you relaunch the optimization, here it's learning a walking gate, but if you relaunch it, the actually optimal gate for that task would be pronking, so jumping optimization. And for that, I'm using stable baseline with the JAX implementation, which everything is also open source and on the DLR. And here I'm directly optimizing at every step. I'm doing one gradient update also because the optimization, the algorithm is quite fast. And that's what you can see. So after 10 minutes, it's working. It's not perfect. You will see it's still dragging its leg. And that's one of the pitfalls of reinforcement learning. If you want to do what you would like, then you need quite some reward engineering. And you cannot really control what's going to be learned, so you need to be, it takes time, and then you will need to relearn from scratch every time. And this is the final gate after only 30 minutes of training, but you see that it plateaus already after 10 minutes. So it's possible, but that's not the optimal way to bring this. And my approach is particularly targeted toward beds, and the idea is, even though I'm not optimizing for using the elasticity of the robot, because the optimal way to use that robot is actually to use the elastic actuation. My hope was that by using learning a model-free algorithm on this quadruped bed, we would exploit the elastic actuator without explicitly doing it. And the approach I'm taking is, instead of learning from scratch, I'm giving more structure to the learning, and basically I have a basic nominal gate that I can generate with different things, and here I'm generating it with CPG, so coupled oscillators, and I'm refining that open loop policy, open loop control, with learning on top of it some data using reinforcement learning. So closing the loop to further improve performance or improve stability in the case of pronking. You've seen it this morning, but I will show it again. This is what you can achieve with a pure open loop policy by optimizing directly on the real robot. You will match the natural dynamics of the robot, and you will be able to have efficient pronking. One thing you may have not noticed is this robot is actually not the same robot as this morning. It's a robot with a different stiffness, but because the approach is model-free, it still works on that robot. And it works not only on that robot, but it works also on the new BERT, which is still in development. So that's the third robot. You just apply the same components, so having trajectory generation, optimizing it directly on the real robot, and then applying reinforcement learning. And the other nice thing with this approach is you can choose what gates you want to learn, what gates you want to optimize for. I've shown that also this morning, is you can easily switch from going forward to backward for turning also, despite it misses the hip joint. And this is something that you would require lots of reward engineering, where here it's by design, you can choose the gate, and what I'm actually also doing now is not only having fixed gate, but also letting the robot explore what is the most efficient gate, or what are all the possible gates that are achievable for that robot. And that I'm doing it by directly optimizing on the real robot. So as I said, the first component is using trajectory generation using a central pattern generator, which is mainly 4 coupled oscillators, so 1 oscillator per leg. And then you have some parameter that you can optimize, like the step length, the swing and stance duration, and the ground clearance. For that I'm using black box optimization, which allow actually to quickly learn the optimal set of parameters directly on the real robot, using actually Bayesian optimization in that case. And this is what it looked like. So the nice thing is it does a global optimization. So it's not only optimizing, it's not only finding one controller or one solution, it's finding a population of solutions. And then, because I'm logging a bit everything, I can sample from it to achieve different speed or different gates. And if you compare it to tuning it by hand, in 10 minutes you already obtain, you already go faster than what it takes for a human in 1 hour to tune it. And if you let it run even faster, then you get even faster gates. But open loop policy is a bit unsatisfying. It's very nice that it can run on the hardware, so you can further improve performance and stability in the case of pronking using reinforcement learning by closing the loop. So the desired position of the leg would be first the open loop position, and then you close the loop with RL to compensate for I don't know, asymmetries, or for taking into account actually the state of your robot. And at the end, this is what it looked like for each leg. So you have the open loop component, and then you learn some residual correction using reinforcement learning. And this is what it looked like. So the blue one is the nominal trajectory generated using the optimized CPG, and then the orange one is the one after adding RL on top. And you may think, okay, the difference is not that much, but if you look at the performance on the robot, actually you go 30% faster in only 15 minutes of additional training. So it's slight modification, but which give you actually a nice boost. And let me just show you quickly additional video. So this is what it looks like if you tune it by hand, and you can achieve that in 10 minutes. And by letting it optimize directly on the robot, you can go 60% faster by using exactly the same joint velocity limits, which means that it's using using the elastic joint. And here you see the stabilization of pronking, so like having a only open loop policy for pronking will only work up to a point, but as soon as you destabilize it or have some disturbances, then it won't work anymore. So adding RL here help stabilizing and avoiding also the drift for the robot. And by combining the two, so both optimizing the trajectory generation using black box optimization and adding reinforcement learning for closing the loop, you can actually achieve the fastest walking gait that we have on the robot. And here what you see is that even on the Antuned CPG, Antuned trajectory generation, if you add reinforcement learning, if you close the loop with it, then you can still achieve better performance. And you go 30% faster. So I have two last things to show, and I think I'm just in time. One thing is comparison of all the different combinations. So using open loop policy only, open loop with RL, and then optimize open loop with RL. And you can see actually on the same track at which speed they are. And the last thing I want to talk about is what is the learning algorithm actually exploiting or not the elasticity. And this will be my last lesson. So at first you have learning from scratch on the left versus just Antuned CPG. So learning from scratch with RL is actually the slowest one and doesn't really give this good. And then you can add RL on top and you go already 30% faster in 15 minutes. And again, all is done on the real robot, so there's no sim to real transfer. If the learning works, then I can just reuse the train policy. There's nothing to do additionally. And finally, you can combine everything, optimize the trajectory generation, plus add some closed control, and you will obtain the fastest gains. And this is the last, but also very interesting slide for me, which is comparing the joint and motor velocity for that. So in a normal rigid robot, the two joint and motor velocity will be the same, but in bed, because we have the elastic component, we can actually store energy and release it later to go faster than the motor. And this is what you can see. So in orange, it's the motor velocity, which is capped at 4 radians per second. And in green, you have the potential energy of the spring, and you see that when the potential energy is released, you will get the maximum joint velocity. And if the timing is correct, is done, and matches actually the dynamic of this elastic robot, then you will, here it goes actually at 4 radians per second, so the joint goes twice as fast as the motor by only using this storage and releasing it at the right time. And this is interesting, so it was not optimized for it, but because it's using directly the real hardware and because it's optimizing for performance, the only way to go faster is actually to match the dynamic of the robot. So I hope I convince you that we should learn a bit more on the robot, so it's not orthogonal to learning in simulation, that we can exploit elastic actuator using learning algorithm. And the nice thing is doing model-free learning, you can apply it on different robots without much change. Thank you, and if you have any questions. Yes?
Which reinforcement learning algorithm you use?
So I'm using a recent extension of soft actor critic, which is called DrawQ. So a soft actor critic with dropouts and layer normalization with a lot of sampling of the replay buffer, which make it sample efficient.
What is like dimension of like the action and space?
So action space is a dimension, so 2 dimensions per leg, and the observation space is a stack of 2 frames, so to compensate for the Wi-Fi delay. And it's around, I would say, 30 dimensions because you have the joint position, velocity, torque, and probably the IMU. So it's probably around 60 dimensions.
I think this is why you can run it learning in the real robot. You don't need the simulation. So basically the space is quite small.
Well, it depends to whom you talk, but yes.
Are you able to take this and put it into Sim? Are you basically, is it set up so that it will only run on the hardware?
Recently I finally managed to have the simulation also running to actually quickly visualize what has been done. And I have only the open loop part running on our application. But it's quite some work actually, and if it runs on the real hardware, why would I spend so much time on this simulation?
So if you, okay.
There was one question here, and then here, but yeah.
Me?
Yeah.
Okay. How quickly does the learning drop off when you're running on the real robot? You said
Plateau?
10 minutes. Sorry, what was that?
When does it plateau? So for that robot, for that task, it plateaus in 15 minutes.
Okay.
But it highly depends on your reward function and what you say. But here I'm really using the simplest one to show actually that still using a simple reward function, you can learn the behavior that you want. You just need more structure and a bit more knowledge and not learning from scratch.
Just to add on to that, for your reward function, are you heavily, or I guess that's not your reward function. How high do you set your velocity to when you're trying to train it? Do you ramp it up to try and match above 0.36, or how does that work?
I'm not sure to understand your question.
So it's trying to track your reward function. It's trying to track the velocity of the center of mass, right?
My reward function is just maximizing the forward speed of the robot.
Okay, gotcha.
So it's not even tracking it.
Okay.
So there was a question on the left and then on the right. Yes.
Yeah, I just wanted to ask, did you ever try model-based optimal control using the full model and compare that to your?
No, I didn't have the time, but the other problem is also we don't have a perfect model of the robot.
You did not have it, or?
No, and that's actually one of the thing is with this actuator, you would have to model also the friction, you would have to model the friction of the motor, of the gear, friction of the bed. You can have a model of the robot, but you can talk with Davide. Yes, he has some hard time sometimes transferring what he learned in simulation. That works quite well, and then he tries on the robot and he complains about the friction.
Control the motors only in position. The bandwidth of the top controller is extremely low. It's difficult to control torque or do some fine movement.
So there was a question in the back.
Thank you for the nice presentation. You said that you have the CPG and you mentioned it as a feed-forward or open-loop controller, and then with RL you said that it's kind of closed, but is it really closed because it's kind of optimization of the CPG and yeah, it can...
So it's directly changing the desired foot position. And the RL is using the state of the robot as input. That's why I'm saying it's closing the loop.
But if, for example, there's a kind of perturbation or something, can you immediately respond to that?
Yeah, that's the point of adding some this term, is that it will compensate for any perturbation, or it will also compensate for any accuracy or asymmetry in the robot. there was
One more
one.
question, Mayor, and this is the last one.
Yeah, I'm just curious, like, this is super cool. I'm wondering if you've thought about or you have any philosophical thoughts on like learning from scratch and just kind of doing the policy learning versus actually trying to do some sort of SysID and learn a model and then do model-based control.
I'm actually a bit doing both. I have a skill which is all about identifying the model and learning from data the model,
Yeah.
and we'll see how far we go. Yeah, for me, it's both approaches are valid. It's just that if you manage to do it with model free, usually then you can apply it to not only one system but to many other systems and quickly change. Where yeah, if you learn model based, usually you need to well, if you do system identification, you need already a model and change it every time you change your model.
I mean, it's the same thing, right? You're learning the policy from scratch on the new robot. I'm saying you learn the model from scratch on the new robot,
Okay.
and then you can recycle that to have new policies
And-
for tasks or whatever. Right?
And here, actually, I would expect it to be quite hard because when you learn with hybrid dynamic, especially with the contact forces, this is pretty hard to measure. I would say. So, where here also you don't want to learn the full model, you just want to learn a policy that works. And
Yeah.
I would guess it's probably easier.
Yeah, I'd be very curious to see someone really do it on the same robot, so I'm glad you're doing it.
And then there was a last question.
Yeah, when you optimize the CPG plus reinforcement learning, you initialize with the CPG, right?
Yeah, so the idea is that I optimize first the CPG, I fix it, and then I can use reinforcement learning on top.
Do you think it would be equally valid or potentially give you different results if you tried to optimize both at the same time?
Actually, there was some work where the reinforcement learning was not changing the output, but directly changing the CPG, like changing the pulsation or changing also the state length, but in a dynamic way. And this would be also valid. It's just this ensure actually it prevents the RL from deforming it too much, and it keeps the gate that you want. Because if you give too much freedom, then RL will take over and will just do whatever it wants, and you will lose actually the structure that you try to enforce.
Are variables.
Are you sure that RL will lose the structure you want to enforce, or maybe are you sure you need to enforce anything? I mean, shouldn't RL or some optimization be able to do everything?
So if you have a simulation, yes. But if you want to learn in 1 hour or less, you better have some structure. And I did some also other work on learning to race, and I was giving my driving as a baseline and letting the RL learn on top, and I was letting the RL also choose how much of my driving it was choosing, and very quickly, even though the RL was a bad driver, it would put my driving to 0, because it would be more predictable for it to only have its driving. So yeah, that's at least that's what I got from some experiments, that if you give too much freedom to the RL, it will remove the structure that you're trying to enforce. And yes, you can give a lot of freedom, but if you don't give enough freedom, then it will take forever to converge.
Well, it just seems to me that, so RL is going to head towards an optimum, and then a CPG plus RL then sounds to me like it has to be suboptimal, unless the RL basically has some way of undoing the CPG.
That's true, but also RL we tend to also converge to local optima, so you are not guaranteed at all that RL will converge to the global optima, and by giving a bit more structure, you are already guiding also the optimization. But of course, here the assumption is that your nominal behavior is already close to optimal, otherwise you will be far away from the optimal.
Think of it as a warm start.
Okay, guys. Very quick announcement.